Hello, good afternoon, everyone. My name is Peng. It's my great pleasure today to present our team's recent work named as AITER. So let's move forward. Okay, so today we will mainly cover the 4 topics here. Number 1 is the AITER's architecture, why it is robust and ready to serve the developers' use cases. Number 2, we will show a simple example that demonstrates how you, as a developer, that can integrate AITER with your end-to-end workloads or your model scripts or your own inference engines or frameworks. Number 3, we will pick up Triton backend as an example to show how you can develop your own logics, your own AI operators using AITER harness and using OpenAI Triton. Last, we will show you how you can make your decisions to say if you want to pick up a high-performance operator from AITER directly, or you want to develop your own, and how. Okay? So this is a one-pager for AITER. AITER represents AI tensor engine for ROCm. It's a robust, centralized hub for high-performance AI operators. We developed it in agility in mind, which means we make it fully open sourced. And every and each features we develop on AITER is open source. There's no private branch for development, even for our new silicons. So today you saw Dr. Lisa Su's announcement on MI350, and actually all the high-performance kernels were developed using AITER harness and all in public. So you can go there. If you have access to 350, you can run those workloads today. So that's how our vision in AITER to be a fast evolvement and a vehicle for AMD to deliver the best in-class AI operators for you as a developers. So AITER supports a great series of the operations like the prefill attention, decode attention, fuse MOE, low precision jams, customize or reduce all those essential pieces that you can use to form up a high-performance large language model and generative AI. It also provides both Python interfaces and C++ interfaces that can be easy to adopt in your use cases on whichever interface you prefer. And in the backend, AITER uses all different technologies AMD can provide to form up a high-performance AI operator, including our C++ template-based programming language called composable kernel, CK, or HIP, or even assembly, and the OpenAI Triton. So then all those operators written in those different approach mapped to a compiled binary that you can be ready to deploy for your use cases. Okay, to be thorough, we also want to clarify that AITER is not supposed to be the large language model service engine or training framework or just a graph compiler. It's not a thin wrapper or existing high-performance libraries as well for ROCm. Okay, so here is a very simple example to show how you as a developer can integrate AITER in your use cases. So AITER provides Python APIs as a main interface of support. We already have AITER integrated with vLLM, SGLang. You heard from Lianming just now. You will also hear from Simon in the next talks. So we use AITER to plug into the server engines and move the most expensive computation blocks onto AITER. And that way we can greatly accelerate the workloads on AMD GPUs. And also there's a lot of clients have their internal frameworks. Previously, it was pretty difficult for AMD to point them to high-performance operators before AITER age. But right now, we just point everyone to AITER, pick up the operator you want, and integrate using our existing interfaces. So that makes things much easier and much more efficient. So here we provide a very simple implementation of linear layer, and you can import AITER as a regular Python package. And this one represents a pre-tuned gem for the target silicon. And you can just import it and define your functions as usual. That's it. Then you have the AITER functions replace the original Python calls, and you get the instant acceleration. Okay, here we want to demonstrate a little bit on how we were able to achieve the end-to-end performance enhancement with AITER project. So we did a day 0 launch for DeepSeek, and soon after that, the team identified a few hot spots that we think we can do much better in software efficiency. With that one, the team has spent critical effort to do the profiling, analyze the cycle by cycle how those current operators working, and then we came up with a better pipeline, better design for those critical pieces. So we listed 4 operators here, but we actually did more than those. That includes a block scaling gem, fuse MOE, prefill multi-header attention, and the decode MLA attention. So as you can see on the chart, we achieved from 2x of the improvement to an amazing 17x, thanks to the AITER kernel high performance pipeline. And on the end-to-end front, we were able to achieve twice of the throughput thanks to AITER. And this is not a standalone case. We actually use the same approach that did the day 0 launch for Llama 4, Q13, and many other state-of-the-art models with AMD GPUs. Okay, this one shows how we use AITER to shift left and accelerate the key operator performance on new silicons. So we mentioned MI350 launch. And with AMD's current commitment to do a yearly refresh of the silicons, it's getting increasingly critical for AMD to do shift left on the kernel design. For example, those flash attention forward and backward kernels, we actually did it soon before the silicon was back. We did it on the emulator, and we designed the kernels with all new hardware interfaces in mind, hardware features in mind, including the expanded LDS capability and the throughput, as well as a doubled MFMA rate and the 2x of transcendental rate. So with those one, we were able to achieve amazing gen-to-gen performance uplift. Those are measures from end-to-end workloads. Using MI300X as 1x, we were able to achieve up to 4x on forward pass and up to 3x on the backward. Okay, so here we pick up OpenAI Triton as an example to show how you, as a developer, can do your own customized operators and how that can be helpful for your use cases. So Triton is a Python-level programming language that can get you to high-performance operators by just write Python code. Prior to Triton, you have to be a very hardcore C++ engineer, very familiar with GPU architecture in order to write such kind of GPU kernels. So with that one, Triton has also been fully integrated into the PyTorch harness. If you are familiar with PyTorch and the inductor backend, in the backend, they use the Triton to generate the fuse kernels. So here we want to show something different approach here on how you use Triton to build your own high-performance operators. So basically, Triton can produce much more features than our standalone libraries here. So for example, we use HIP+LT as a baseline. It supports very robust IP16 and bflow16 on MI300X silicon. However, when we get to some new client, new use cases, they would like to use int8. And while our HIP+LT team ramping for new features, we can use Triton to take a few days and get to some implementations ready for deployment. Right, so time to solution is extremely critical for this, this ever-evolving industry. So we see Triton can be a faster prototyping vehicle and get you the performance sooner. And use the AITER harness, you can get the Triton kernel drafted and use the auto-tune infrastructure to pick up the best solvers or configurations for your needs. Here we showed 2 examples, one from Llama 3 405B, the other for Llama 3 8B. Okay, and this for this page, we show another good example to see how you can AITER to shift left on your optimizations. So we use Advancing AI 2025 as a line here to cut. We were able to use Triton to achieve the close to the roofline jam performance in a much shorter development time. With that one, we were able to form up a very performant Llama 345B, and use that one, we achieved amazing 35x gen-to-gen improvement, as Dr. Lisa Su demonstrated this morning. We expect K plus LT, once they fully ramped up their features, it will be faster, probably 15% faster. And we will be ready to shift to K plus LT when it's ready for production, when the ROCm 7 GA becomes available. However, the key values, again, time to solution, can be greatly demonstrated here. And using AITER, we are ready to shape those solutions in a much more efficient way. On the right-hand side, is also a good example with the Llama 345B. So with the IP4 support, the throughput for the critical jam or metamorph operations get greatly improved. So we sort of cut half by half if you go with lower precision. But as you go shift to the right-hand side, the non-jam operators actually getting exposed. So only with Triton's fusion techniques, you will be able to fuse those actual kernels into smaller kernels, small actual kernels like element-wise, softmax, those kernels, you can fuse those and get into one big kernels, or fuse it to the jam kernels. That way you can, if you look at the rightmost side, we were able to greatly reduce the time cost for the non-jam kernels and shift back to focus to jam. And then we can apply further optimization and get the final performance we would like to see. So those are a great example to show how you as developer can use Triton and AITER harness to develop your own kernels and achieve the good performance sooner. Okay, this is the last page. I would like to demonstrate how you guys can make your own design decisions whenever you need to access to high performance AI operators on AMD GPUs. If the kernels you are looking for is standardized, is ready to pick up from existing high performance libraries, go for it. You are guaranteed to get the good performance with either AITER or K plus LT, MLOpen, or ROCm. However, if you would like to get some customized kernel and you are comfortable to write Python level programming languages, go with OpenAI Triton harness. And get it integrated with an AITER library. You can take advantage of the CI/CD, auto-tuning, and all those different interfaces that we can offer. And if you are hardcore C++ developer, you are comfortable to write C++ code with composable kernel, go with that one. The development cycle might be a little bit longer than Triton, but you have much more knobs you can have in control and do your development in an efficient way there. And if you have great GPU architecture knowledge and your problem requires the last 5% performance to secure those ones, go with either HIP or assembly. We have some great example to be published in AITER project to demonstrate how we use assembly to develop and get the best performance possible on those most expensive kernels. So yeah, hopefully you guys can understand what is AITER and how it can accelerate your development on AMD GPUs. Thank you. I think I'm ready to take some questions if there are any. Yes, please.
Do you think Triton will ever catch up with it, or is there always going to be like an offset? And Triton, do you see that gap narrowing?
Right. So just repeat the question. The question is, do you think the Triton is going to catch up with HIP or the other programming languages, or the gap will always there? So I think the way I see this is that Triton is improving itself. There's a tons of MLIR-based compiler techniques has been added into Triton pipeline, especially with the AITER assembly kernels. Our Triton compiler team is actually learning the optimal pipeline we developed with the assembly kernels and pick those we named the 8-wave, pick it back to Triton compiler and get the performance greatly improved. So Triton side has been improving. However, the way we look at it is that the problem definition will change as well, right? So the optimization you put on this problem, you can catch up with the Triton compiler for a problem, but there's the other problem you want to tackle. And you want to have a time to solution. Triton can be flexible to get there. However, if the same amount of effort is putting for the the more performant options like CK or HIP, you probably get that performance as a higher bar, but eventually Triton can catch up there. Yeah, thank you. If no other question, I think I'm good. Yeah, thanks everyone for having me here.